Chapter 15 is all about solutions and concentration of solutions and how that works in chemical reactions. We did a lot of work with aqueous solutions in our discussion of kinds of reactions, and all of those aqueous solutions have a certain concentration. So we're going to keep our discussion going in chemistry. The videos are going to be kind of looped together. So the first one is going to be on why things dissolve. Then we're going to talk about the quantitative terms associated with concentration of a solution and the mass percent, which is sometimes seen as mm percent. So that's going to be in the second video. We'll move on and talk about the concept of molarity or concentration. That's the big M that you've seen maybe on a label in the lab or something like that. We'll also then learn how to calculate the concentration of a solution if you mix two solutions together or dilute. And so there's going to be a new equation for us to take a look at. And we'll talk more about that coming up. And the last part is to roll this all in together with everything we've done through chapter 8 and 9 and stoichiometry. And now we have a new way of calculating the number of moles. So if you think back to chapter 3, we first were introduced to homogeneous mixtures and said they are also called solutions. They have a variable composition. They're not the same all the time, but they are the same throughout that beaker or bottle or whatever it is. So common examples would be coffee or tea, the air that you breathe, tap water would be a mixture. Mixtures or alloys of metals are also an example of variable composition but the same throughout, or a homogeneous mixture. There are a bunch of terminology or a bunch of words that associate with solutions. And so solution is a homogeneous mixture formed when a solute dissolves in a solvent. So the solute is what you're dissolving. So maybe it's the Kool-Aid powder in the water. It's usually present in a smaller amount. Where the solvent is what you're dissolving it in. It's usually a liquid, as in the case of a lot of ours when water was a liquid, sorry, those are aqueous solutions, and this is usually present in a higher amount. You think often of liquids, so this is your solution in a beaker, but we can have solutions that are gases, dissolved in gases, so the air you breathe is an example of that. You could have an example of solids being dissolved in solids, and so brasses or metal alloys could be an example of that. And then the classic that you probably were thinking about, Kool-Aid or sugar or whatever dissolved in water. We have the different states of the solute and the solvent. We can also have a gas dissolved in a liquid. And this is the case of a carbonated beverage. Under pressure, that gas stays dissolved in the liquid. And so that is another liquid solution. An example of that might be a pop. Okay, so identify the solute and the solvent in these examples. So a saline solution, that's NaCl or salt and water, where the solute is salt and the solvent is water. Here we have an example of that gas dissolved in liquid, so carbonated water and CO2 is the gas. The CO2 is what's dissolved in the solvent, which is water. Unless otherwise stated, most of the solvents that we will talk about will be water. Those were all the aqueous solutions that we were talking about. Anytime you saw that AQ after a compound, that means that that compound was dissolved in water. So a lot of that's review, and a lot of the next page is also a review. So talking about why things dissolve or what governs solubility, we need to roll ourselves back to the thinking of chapter 12 and the kinds of chemical bonds, because the rule about what dissolves in what is really based on the concept of the kinds of bonds, or understanding these things on a molecular level. So as a review, ionic bonds, so if we had an ionic solute, so a salt, or any ionic compound, occurs between a metal and a non-metal. If this feels like review, that's great because you've totally done this before. It results from a transfer of electrons. One thing, usually the metal, will give up electrons and the non-metal will gain the electrons, one becoming a cation, one becoming an anion. If the ionic substance is dissolved in water, they typically or can break apart into their ions. And more on this later. We have already talked about that too. In contrast to ionic bonds are covalent bonds. So covalent bonds happen between two nonmetals. So two things from beyond the step. They were named in nomenclature with the prefixes like carbon dioxide, carbon monoxide. It involves a sharing of electrons. There are two different kinds of covalent bonds as we talked about. We could talk about nonpolar covalent bonds. So the first kind would be equal sharing. Because the two things are exactly the same or are very similar in their electronegativity, it results in no polarity or no polarization. Oops, spell this right. Of the compound or the molecule. So obviously all the diatomic molecules, so oxygen, chlorine, nitrogen, any of the diatomics, any of the Hofbrinkels, or any hydrocarbon. So the electronegativity difference between carbon and hydrogen is not enough to bring polarity to hydrocarbons. So hydrocarbons, think anything that typically burns. So propane is an example of a hydrocarbon. So the other kind, we already talked about the nonpolar covalent bonds, which were equal sharing. If we have unequal sharing, it leads to a polarization or charged regions, sometimes called poles of the compound or molecule. So typically it's anytime we have oxygen in it, it really does lead to this polarization or these polar molecules. So water is a classic example. There's more on the next page of that. Any alcohol in biology, any functional group, lets molecules be dissolved in our blood or in our bodies. If you think back to your chapter 12, there were other ones. And so this idea that, you know, the polarity can happen in molecules. So the polarity of water is particularly interesting in biology, but it is a really good example of polarity. And so in oxygen, there's a really high electronegativity, or they really love electrons. And so this sharing of electrons between the hydrogen and the oxygen, and I've drawn this out back when we were drawing Lewis dot diagrams, they share to get a full valence shell, or the octet rule sometimes it was called. But oxygen is more electronegative. It's really greedy and it hangs onto those electrons for more of the time, more of its share of the time than the hydrogen. So this leads to a partial negative charge on the oxygen atom and a partial positive charge on those hydrogen atoms. And this results in a polar molecule. Okay, so hang on to that idea of charges. We're going to talk now a little bit about how ionic compounds can dissociate or dissolve, or what the difference is between those two in water. So ionic bonds have strong bonds, but they also easily dissolve in water. The positive hydrogen atoms in water are attracted to the anions in an ionic compound. And the opposite is also true. Those negative oxygen atoms in water are attracted to the cations in an ionic compound. The process of separating the ions is called dissociation. In our notes, we talked about how dissolving was not the same as dissociation. And we talked about how covalent things could dissolve but not dissociate. So the classic example is sugar will dissolve in water, but it does not dissociate into its ions. So here we have an example of an ionic compound dissolving in water, dissociating into its ions, its anion, or its cation and its anion. So all of these can be written that way as dissociation equations. It's like what we were doing in the net ionic equation. So calcium chloride will dissociate into calcium ions in solution and 2 chloride ions in solution. This should be, again, a bit of a review or a recap back to those complete ionic equations. So the last one, the iron 3 nitrate, is going to come apart. It's going to dissociate in water into the iron 3 ions and 3 of the nitrate anions. So a little bit more, now that we've understood a little bit of the bonding, and again, most of this is a recap or review, seeing it kind of in place in this chapter on solutions, we need to understand why all things don't dissolve in others. And if we take a look down to the molecular level, like things dissolve in like. So what we're talking about here is things that have charges will dissolve in solvents that have charges. Things that have no charges will dissolve in things that have no charges. So if we think back to the kinds of compounds that we could have in the charge regions, well, ionic compounds. The other thing that have charges are polar molecules. This is how salt can dissolve in water, right? That's an example of those two. So in the world of no charges, if we were kind of group things like and non-like, anything that is non-polar is all that will dissolve in a non-polar solvent. So like it said in the notes, most of our solvents will be water. So here we go with this. So polar substances will dissolve in polar substances. The example of that would be alcohol in water. Alcohol has a hydroxide group on it, and water has polarity to it. And so these are this is a polar substance, and this is a polar substance. So those are examples of like dissolving in like. Non-polar substances will mix in other non-polar substances. So this is the example I could give is blending oils, right? Mixing maybe some grapeseed oil in with your olive oil if you're making a fancy dressing. Polar and nonpolar substances do not mix in each other. They are not like. And so the classic example here is oil and water, where oil has no charge to it, it's nonpolar, and water is polar, it has charges. So this is how things are alike if you kind of like segment out the different kinds of bonds and the different kinds of molecules. There is a little bit more in the crash course if you want to check that out. Again, I'll post that at the bottom of the Moodle section. So some more terminology. We've got solvent, solute. We've got this idea of how like dissolves like. We could talk about a solid dissolving in a liquid, and that makes it soluble. We could talk about how a solid doesn't dissolve in a liquid, and we call that insoluble. If we have two things mixing, two liquids mixing, and they are capable of mixing, like the two oils from up here, we say that they are miscible. If things don't mix, like the oil and water, two liquids don't mix, it's immiscible. And so down here we have a bit of a chart where it makes you really think about the like dissolving like, and here we're supposed to practice using those words of soluble, insoluble, miscible, and immiscible. So if we have a polar liquid in a polar liquid, so we're mixing this and this together, that would be the same. And they're two liquids, so we'd say that they are miscible. If a polar liquid, as the solute, was trying to dissolve in a non-polar liquid, that would be immiscible. Non-mixing. Down here we get some more examples. So I like practicing these words, and then we'll practice the examples as well. So non-polar liquid in a polar liquid, that would be immiscible. They are not alike. Where a nonpolar solute in a nonpolar liquid, that would be miscible. They would mix because they are the same. Okay, things get a little bit trickier here. So we've got a polar covalent solid solute in a polar liquid. That would be soluble. We switched from the words miscible and immiscible because we're not talking about liquids mixing together. We've got a solid in a liquid. A polar solid in a nonpolar liquid, that would be insoluble. They are not the same. A nonpolar in a polar, again, we're in the world of solids in liquids. Insoluble. And then a nonpolar solid in a nonpolar liquid. They're alike, so we'd say that they are soluble. An ionic solid in a polar liquid, so this would be a salt in water. I would say soluble, but I'm going to give a little bit of an asterisk on this one. So there'd be a bit of an exception for this because we remember the solubility chart. When we were talking about precipitation reactions, we looked at a chart to predict if an ionic compound was soluble or insoluble. So theoretically, they are like, and they would dissolve, it'd be soluble, but there are those exceptions on that solubility chart that made the precipitates. Okay, and then the last one, an ionic solid in a nonpolar liquid would be insoluble. Okay, so let's take a look at these. So would these be miscible, immiscible, soluble, or insoluble? And I like categorizing them. So water and alcohol, that's going to be miscible. But why? We know they mix. So what we have here is a polar liquid in a polar liquid, right? They are miscible. That was the first example up here. Gas and water, they don't mix. We know that. We'd say that they are immiscible. But on a molecular level, why? So gasoline is a hydrocarbon. It would be nonpolar, where water is polar, and that's why they are unlike and they don't mix. Sugar and water, so soluble or insoluble. We know that sugar can dissolve in water, so we'd say soluble. But again, why? And so what we have here is sugar, C6H12O6, is a polar molecule. Anytime you have that oxygen in there, it's going to be polar. And so it's a polar solid in a polar liquid or solvent. Okay, sugar and oil. Have you ever tried this? Sugar in a gas tank, maybe? So we have a polar solid in a non-polar liquid. Oils and gases, they're back into the world of hydrocarbons, and there's equal bonding in here. And so in that one, I would say insoluble. Sorry, got the wrong word. So the key thing here is to get these words out of the concept or out of the example, but I'm trying to give a little bit of the background in there. So give these ones a try. I'll put the answers up. And if I talk through these ones, why did I give these answers? So salt would be ionic in a polar solvent. So we've got this idea of charges. Remember I said they were categorized as like. So salt is ionic. In water, also a polar substance. So that's why they can dissolve. So salt, I'm talking specifically about NaCl, not a general salt, because an ionic compound in water, mostly. Remember, this was that asterisk that I gave up here. So depending on your solubility chart, you could say if it's soluble or insoluble. And then sugar in propane. So sugar is polar. where propane is nonpolar. It's a hydrocarbon, and so it shares equally like the oils and the other hydrocarbons that we've talked about already.